interactions. If you remember, in chapter 1 we had Lewis structures, but they couldn't account for the electron delocalization. And in chapter 2, Vesper theory couldn't predict the extended molecular geometry. But in chapter 3, we can help with explaining hybridization, sigma and pi bonds, cis and strands, constructive and destructive interference, and energy orbitals.
Hybridized atomic orbitals. So why do we have hybridization? Let's use methane as an example. So right here we have a central carbon in the middle that has 4 electrons that is bonding to 4 different hydrogens. However, when we see that these electrons are of equal energy, we look at the electron configuration and it doesn't make sense. We have the 1s orbital, 2s orbital, and 2p orbitals. And the 2p orbitals have a higher energy than the 2s orbitals. So looking back, we can't really say that they're similar because we know that carbon has 4 electrons of equal energy. So what happens is that the 2s orbital and the 2p orbital hybridize, and you have 4 equal electrons that carbon uses to bond to 4 different hydrogens. So looking at the electron configuration of carbon, you see that the orbitals are represented as boxes, but in reality, these orbitals have 3D shapes. So the s orbital is represented as a sphere, and the p orbital is represented as a dumbbell shape. So how do we get sp, sp2, and sp3? Basically, it's simple mathematics. S plus P equals SP, which is 50% of both being represented. Then S plus 2P orbitals equals SP2, 1/3 S and 2/3 P. Then S plus 3P orbitals equals SP3, 1/4 being S and 3/4 being P. So how does hybridization relate to Vesper theory? So we learned that hybridization is basically 2 orbitals with different energies hybridizing, giving us the orientation of hybrid orbitals. And then you have the Vesper theory coming in and giving us the bond angles and electron geometry. So when you have an sp orbital, the orientation of the hybrid orbitals will be this dumbbell shape, and the bond angle will be 180 degrees, and the electron geometry will be linear. So for sp2, we'll have this shape called the trigonal planar, and the bond angle will be 120 degrees. And for sp3, the big tetrahedral, you'll have this shape with the bond angle of 109.5 degrees.
So after we have known like the structure, how it kind of builds up, and like we have 3 sigma bonds, like 3 sigma bonds, and then like we are having this double bond, which is like we understood as the overlapping of these like orbitals. Okay, so let's see, for example, if we kind of like took these 2 hydrogens, this hydrogen and this hydrogen, and replace them with a chlorine, for example. So okay, so we'll do that, and we go here and change these 2. So we'll put a chlorine here and also a chlorine here. So when we put that, because this overlap is happening like in this direction, and like these 2 orbitals are coming like this, and they are overlapping together like this, we cannot actually like rotate this compound like where this chlorine could come down here without the breaking is overlapping. So like we get this kind of locking, and we have like 2 different like 2 groups like on different sides of the compound. So like if it is like this, one is up there, one's down there, then like we have the what we call as a transposition. So like, which means like these 2 groups are like locked on different sides of the compound. Let's think of another compound where the 2 chlorines are actually on the same side. So this is a different compound where like when actually it was forming, the 2 chlorines were on the same side. So because of this like locking position, we have the 2 chlorines down there, and they cannot move because we want like to break this double bond. So actually both of them are on the same side. So we call this the cis position.
So molecular orbital theory and molecular orbital theory charts were two really big concepts in this chapter. And all molecular orbital theory is that all electrons in a molecule can be thought of as occupying orbitals. And all the charts do is really do a good job at demonstrating like the energy levels and how the orbitals relate to each other. So this is what a molecular orbital energy chart looks like. You put your orbitals on the side, and you put your sigma bonds and pi bonds in the middle. And you can basically break down the molecular orbital chart into three basic rules. You start adding electrons from the bottom to the top. Also, sigma bonds are always going to be lower in energy than pi bonds because sigma bonds have the end-to-end interactions opposed to the side-to-side interactions, and the end-to-end interactions are a lot stronger, so they're a lot more stable, thus lower in energy. In anti-bonding, however, sigma bonds are higher in energy, and that's just because it's the converse to them being so low in energy.
Hi guys! I just want to give you a quick recap about everything we learned. So, simple addition of orbitals, S plus P equals SP. Geometry shape of molecules, we have, tetrahedral, trigonal planar, linear, and their angles. We also learned trans and cis. Cis being on the same side, trans being on the opposite side. We also learned pi bonds and sigma bonds. Sigma bonds are head-to-head, and pi bonds are side-to-side. We also learned how to draw energy diagrams, and now we get it.